Good evening, y'all. Welcome back to another Sunday Night Electronics Bash Electronics class. I'm Jeff. For those who've been here a bunch before, it's good to see you again. For those who have not been here before, welcome. As always, we'll get the timer started here. We'll give folks just a few minutes to catch up. Hi, Nate. How are you? Hi, Palmer. Yeah, you guys know the deal. We'll give folks a few minutes to catch up here before we dive into the business of tonight, which is doing visual displays on screen. We're going to actually draw on our Raspberry Pi monitors tonight and make things happen. Good to be here. Yeah, I'm glad to be here too, Nate. It's weird. I was saying to my wife again, and I think I said this last time we were together a couple weeks ago. Somehow, like 1 week felt like all of these classes were stacking up on top of each other, and somehow in 2 weeks I sat down and I'm like, what are slides? How am control? So it's all, I mean, time is super squishy these days, as we know. It's all very strange. But it is good to be back. Tonight, I am drinking a, there's always glare. I have this like very bright light you can see as I get close to the camera there. I'm drinking a Le Jus from Alarmist Brewing Company here in Chicago. It's a hazy, juicy, New England style IPA, something. It's the very popular style of beer where it's all super hazy. But I just love it so much. Like I love sweet things. I love sweet and juicy things. So like the fact that the trend now is to go sweet and juicy, I'm not too sad about. I can even mute myself now, so you don't have to listen to me slurping. Thanks to my new. Oh, thanks, Palmer. Yes, I got it. I have my lav mic on. And this week I got in my audio interface that it attaches to. Thanks again to Nate for hooking me up with some gear to help this go a little bit more smoothly. And weirdly, one of the things I've noticed is like how big a difference in volume, like input volume there is. I mean, it shouldn't be a radical surprise. I was using like the combo headphone mic input jack on my computer before, and the preamps on that, no shocker, are just dookie garbage from a toilet. And now with an actual USB-C audio interface, there's like a lot more control of the gain structure of things going in. I think the preamps also just sound better. But I also am covering up underlying noise with background music, so I'm kind of cheating in both ways. But thank you. Yeah, I'm glad it sounds good. If it ever stops sounding good, to trained ears, Palmer, or untrained ears out there, do let me know and we'll figure it out. I'm not an audio professional, so we'll see how it goes. But yeah, no, it's good. It's good to know that it's going to be reliable more than anything, because I hate having the gear go out in the middle of the evening. But yeah, I think it'll be fun. I just as we segue in here in the next 23 seconds, I think I mentioned last week that my thought about last week, 2 weeks ago, my thought at that point had been to do some kind of technical topic and like segue it to a programming topic, which is object-oriented programming. And things I have learned in the last 24 classes is that would have been a big bite to take off of like given that I wanted to talk about visual representations and visual displays, it was going to be too big of a bite to try and do object-oriented programming, which is a thing that like whole books are written on, and introduce these visual ideas in the same topic. So we're going to do a lot of visuals and a little bit of object-oriented programming, because the visuals will be a really nice foundation for next week when we talk about object-oriented programming and expand on this week's theme. So sort of at the end of tonight, we'll start getting into building some games and some structures. And with the tools that we currently have, it's going to be a little bit, things might be a little bit awkward, and that'll allow us to, the next time we're together, use some object-oriented frameworks to think about how we might simplify our viewpoint of how we're handling these things. Anyway, this will all make a little more sense as we go along tonight, but I just wanted to sort of preface what we were going to go on about. Next stream, I know it's gonna take me a while to get back into like the right verbiage, but I see our timer has expired, so let's get things kicked off, shall we? Give you a brief overview, and then we'll get into some code. This is This is stream 24 of Electronics Bash, Visual Displays. Today we're going to be talking about the PyGame library, which the name makes it sound like it's only for making games. It's really a general purpose visual display library for Python. Well, we'll get into exactly what it is in a second here. We'll talk about drawing to the screen, circles, lines, rectangles, primitive shapes, also drawing images and bitmap files, PNGs, JPEGs, that kind of thing, and how we can move them around the screen, reshape them, reorient them, and start to build images and interfaces out of them, if that sort of makes sense. So yeah, let's just dive in. The two main libraries that we're making use of for today are, of course, the PyGame library, which if you're installing via pip or via the built-in package manager in the Thani Python IDE that we've been using is just called PyGame. We'll also be making use of the random library, which I'm 96% sure is in the Python standard library, so it should come pre-installed with any installation of Python 3 that you might have. If for whatever reason you don't have either of these, you can install them through the Thani package manager. In fact, just so we all remember that we discovered in week 1 where that is, we go into our Thani IDE here on the Pi, we go to Manage Packages, and here we can see I can install PyGame. Let's find that, and I have it here. You can see on my system here it's already nicely installed, running version 1.9.4. There is a version 1.9.6. They're not radically different. Nothing huge has changed. A couple of little buggy behaviors got fixed, but if you have 1.9.4 or anything in 1.8, 1.9, I wouldn't worry about it too much. And similarly, we can look for the random library, which may not even show up because it's in the standard library. Yeah, so it doesn't even find random because it's just included. Cool. So let me start you off. So this is going to be one of those times where I'm going to say, trust me for just a little bit. What I want to start with is a framework that was going to get us started with PyGame. And it's going to involve just a couple of steps that I'm not going to explain now, just so we can get them started. We're gonna build to them in a little bit, but we need a basic sort of 10 lines of code to get us started and get us showing things on the screen. And what those lines actually mean will become clear just a little bit later. So sorry, you'll have to take this just a little bit on faith as we get started. But let's look at our very basic PyGame Hello World program. And of course, if you are new here, Nate and Palmer who are in the chat, I know you're the opposite of new here, but for anyone out on the internet who might be, all of the code and all of the slides for tonight's stream are on my website, which is pointed out over in the subheader over here, jeff.glass/electronicsbash. This is episode 24. You can find the slides, and you can follow along in the code as we go if that's something you enjoy doing. I'm really going to try and write most of this code as we go, but these are sort of the pre-built examples that we'll be centering around in case it's helpful to look at as we go. So this is going to be our little basic framework. I'm going to breeze through it real quick, and I'm going to show you what it does and how it gets us started. So as we've done a couple times in the past, we're going to start by importing a couple of modules. The PyGame module itself, which has a ton of functionality. I'm also going to import the sys library here. The sys library has a lot of functionality to do with your computer system. So we're going to use it in our case to be able to quit a program from within the program. Cause Python to exit when we do something that we hit the Q button or the escape button, or just hit the X button or the little red button if you're on a Mac that closes a window. That's something we need to be sure that our program will do. So we'll bring in the sys library specifically to do that. It has lots of other functionality, but that's what we're using today. Whenever we start with PyGame, we're going to start by using this init function. We're going to say pygame.init. You see, I tried to do a little bit better job of commenting the code this week. Is load all the main PyGame modules and initializes them. So PyGame actually works with your computer at a fairly low level. By that I mean it integrates with, let me zoom in just a little bit here. It integrates with your hardware. It tries to do hardware acceleration through the CPU and through the graphics card where it can. It's a fairly intelligent system. And because those systems on your computer work differently based on whether you are on a PC or a Mac or a Linux machine, there's a fair amount of work that PyGame needs to do up front to establish, okay, I'm just a piece of code I'm running. What kind of system am I on? What's the graphics card? What is the monitor situation like? What acceleration modes are available to me? And calling this pygame.init function does all that for us in the background. It basically gets the whole rest of the module ready for us to use so that the PyGame bits of code know what they're dealing with as far as hardware. I'm going to define a couple of variables here that we'll use in a sec, screen width and screen height. You might guess those are the size of the drawing window that we are about to create, and we'll create it in this next line here. I'm going to create a variable, and this variable is going to represent basically the window that we are drawing to. We use this function to create that window, pygame.display.setMode. And this setMode method or function, I'm going to use those terms kind of interchangeably as we talk about object-oriented code here. This setMode function takes in not just two parameters, but actually a tuple of numbers. You'll recall we talked about tuples last week. They're like lists that don't change. In this case, what we're giving it is not. So what I want you to notice is that there's two sets of parentheses here. If I take them away, right, if this was a function that took two different values, when I try and run this, I should get an error. Yeah, you'll see down here it says argument 1 of this function setMode must be a 2-item sequence, not an integer. It says, oh, you've given me an integer, this 320 number. What I want is a sequence or a list of 2 items, one of which represents the width and height of the screen object, the window object that we're going to create. So when I give it this pair of things, treat it as one object, one list of 2 items, it will be very happy. I'm not going to run the successful code yet. We'll get through that. I have 3 more lines of code to show you. It's very common in PyGame type programming or in other interactive programming to see something like this. Loop forever, while true, or sometimes you'll see it while 1, because 1 is not 0, and there typically 1 is truthful in this case. Because a lot of times what we're doing when we're displaying something to the screen is say, hey, I'd like to put up this still image or this video game or this moving image or series of images, and I want it to go until I quit the program, hit Command Q, Alt F4, go to the task manager and destroy it, whatever I want to do, but I don't want to have any behavior necessarily inside this loop that causes the loop to end. So I'm just going to enter it into an infinite loop, and then it'll be on me, the programmer, to create some kind of situation, some combination of key presses, say, that allows me to ultimately kill or exit that loop. And that's what this little bit of code is down here. This is that thing that I was talking about that, like, you're just going to have to take just a little bit on faith until we get into how it actually works, but hopefully it's not too opaque. Basically, it's saying we're going to ultimately have a list of events that PyGame is keeping track of for us, and if one of them is of this type pygame.quit, then I want to call this function sys.exit. And this is why we imported that sys library, that system library. Sys.exit just kills your program dead. Just says, hey, whatever this process is, you're done. This is actually a really useful thing for debugging sometimes. If I have a series of code that is a lot of convoluted setup and then a sort of arduous computational step, and I think I have a problem in the setup part, I might do something like do the setup, and then maybe print out all of the results, and then just put a sys.exit there. So I do all the original part, and then I just kill my program before it has a chance to move on to the time-intensive part. So as long as you've imported sys, you can use this sys.exit function anywhere within your program, and whenever you hit it, it will destroy your program thread. It will kill it dead. So we'll get a little bit deeper into what this event sequence looks like here, but just know if you take this bit of boilerplate code, this will get you started in a decent way with a PyGame program. So if we run it, we will get a little 320 by 240 pixel window, because those are the dimensions that we passed in to our function here. It has nothing on it. It defaults to a black background, but you'll see I can in fact quit it by clicking the close button. If I take this code out here, if I just have an infinite loop, when I run this code, oops, unexpected, oh yes, I need at least a little something in my loop so it doesn't get confused, right? So now if I try and close it, I'm clicking there, it actually doesn't know how to handle killing my process. It's like, I don't know, you said to loop forever, and I'm looping forever. In this case, if you get into this situation where you are stuck, in Thani you can hit the big red button, and it will kill the process for you. But the cleaner way to do it, and the more sort of future-proof way, is to include this little bit of code that says, if we get a quit event, we're going to quit. Cool. We run it, we get a window size, and so on. Of course, we can change the size of the window if we want. We can make it a 640 by 480 window. Now we have a bigger window to play with. There's also not necessarily a reason why these have to be in variables, right? We could define the size of our window right in the function call. So I could say I want an 800 by 100 window if you really wanted to, and I have this long skinny thing. Maybe this is useful, if you're writing a program that's monitoring some of your system parameters, and you just want a little window that floats up near the top as you're doing something. Hey, Chris. Yeah, Chris, you've missed a lot. We've made it all the way to an empty window so far. It's pretty great. So that's the gist of creating your window function here. So as we see, empty window by itself, not super duper exciting. Let's draw something on it, shall we? Let's get to it. So I'm going to go back to describing this with variables, just so we have a record of what our screen width and our screen height will be here. And now within our loop, instead of just looping forever, waiting for us to quit and doing nothing, let's add some more functionality. I'll leave this this if statement right up here at the top so we can quit if we need to. But let's do a little bit of drawing on the screen. So the PyGame module has a lot of built-in drawing functions in it. For example, especially for like primitive shapes, lines, circles, rectangles. So let's go through a few of those just because they're a useful place to start. The syntax for those would be something like pygame.draw.circle would be the function that will draw a circle to the screen. It's going to take some arguments that we're going to put here in a second. But what I want you to notice is, so we have the PyGame module that we imported that we can make use of, right? Within that PyGame module is actually another smaller module called draw. And within that module called draw, there is a function called circle that puts a circle on the screen. These things sort of nest down from here. We'll see also in pygame.event.get. So in the PyGame module, there is an event module that has some code for responding to events, mouse clicks and keyboard presses and things like that we'll see later. And inside that module, we have our get function and so on. So inside of our draw module, we have lots of these useful functions that cause things to be drawn on screen. So the circle function, for example, takes 4 arguments. It takes the surface you want to draw to. In this case, I just want to draw right to our screen window. So I'll say I want to draw this to the screen. It asks for a color next. And a color in this case can be represented in a few different ways, but most of the time it's going to be represented as an RGB value represented as a list. So let's make one of those. Let's say my color equals, and let's make it a red circle to start with. So that would be full red, no green, no blue. Right? So I can now use that variable inside my function here to draw a circle to the screen of the color of my choosing. It takes a position in terms of x and y coordinates. Let's make them pretty different. Let's say 450, so 400 in the x coordinate, 50 in the y coordinate, and then it takes a radius, let's say a 25 pixel radius. Now, when I run this code, you'll see nothing particularly interesting happens. It still looks all black. Our circle hasn't shown up yet, and that's because there's one more step to getting things to show up on the screen, and that's to call this specific function pygame.display.flip. What's actually happening when you call a function like pygame.draw.circle or .line or some of the things we'll look at in a second here, you're not actually writing directly to the screen window itself. You're writing to a buffer in the background, which stores all of the changes, all of the pixels, all the colors that will be shown on screen. And it's not until you call this pygame.display.flip that all of those changes are applied to the screen in one big mass. This prevents, in a situation where you're running really slowly, you can imagine, if you had a circle whose position was determined by counting all the stars in the universe, you would want that circle to complete its calculation before it gets shown to the screen. And this just ensures that you do all of your changes and then you apply your changes to the screen. So we'll need to call this pygame.display.flip here to get it to show. Now, before I show this to you, I want you to think about the x, y coordinates 400 and 50, 400x and 50y. If I bring that screen up blank again, just think about to yourselves in your head, and not to be a school teacher about it, imagine yourself, where in this window is that circle going to show up, given the coordinates 450 for x and y. Let's put our pygame.flip back in there, and we'll run it again, and we'll see the circle ends up here. Is this where you thought it would be? So remember, we've got our 600 by 400 window here, and our coordinates were 450. And I did them pretty differently here to illustrate the way that the coordinate system works within PyGame. This is actually fairly common for computer-based graphical libraries of all kinds, but the convention in most computer-based graphical libraries is that the origin, the 0, 0 point, is actually in the top left-hand corner of the window. where you would start to read text if there were words written on the page here. Yeah, I guess, I got you, Nate. Good, that's why I do this demo. The reason that 0, 0 coordinates start in that top corner is that, like so many other things, it's based on the old text display systems, which were some of the earliest used in computing. So your first letter of your first line of text would be in the upper left here, then it would scroll along to the right, then you go down one line, then you'd scroll along to the right. So the x coordinate starts in the upper left and increases as we go right, and the y coordinate starts in the upper left and increases as we go down. And like I said, it can be a little bit disorienting sometimes, especially if you're coming from like a mathematics background and you're used to thinking of the origin being, say, in the bottom left or in polar coordinates or something like that. But just keep in your mind that this was all sort of originated back when things were text-based, and then it'll help sort of ground you in that upper corner there, right? So coming back to our Raspberry Pi example, close this here. If I make our coordinates instead, if I make my x coordinate, let's say 0, and my y coordinate 2, let's make it 0, 0. We'll put a circle there, and we'll run it. We'll see we should get a little snippet of a red circle poking out at the origin up there in the corner. Now, of course, we can draw more than one thing on the screen at the same time. So we'll just copy and paste our circle command here. And let's put some circles in some other places. Let's put one in the other corner, right? So rather than giving it hard coordinates, I'll just put it at the location that is the width of my screen and the height of my screen. So I'll say my circle is going to go at screen width for the x coordinate and screen height for the y coordinate. Let's do one in the middle somewhere, and let's do one off the screen somewhere, just to see what happens. All right, we'll compile that, and we see we've got our circle at the origin. We have our circle down here at the maximum x and y coordinates. We have our circle at, was it 200, 200, and then we don't see the circle that goes off the screen. It's not a problem to draw things that are off the screen. You just don't see them. But they won't throw an error or anything. Let's also mess with color a little bit here. So this color, this my color here, was representing red, but if we change it so it's green, 0 red, 255 green, 0 blue, and I run this here, I get red, green, and blue. They look like different colors to you, Palmer? In my display, they looked all red, and now they look all green. Anyone else? Are they showing up consistently? If they are, it might be a weird artifact of the stream. I'd be curious. So we can see sort of by changing this variable my color, right, we've affected what color the circles are being drawn as. I can also, of course, define the colors right here in my function call, right? So I could say draw a, in this case, green color here, but if I instead put a color value directly into my function, like maybe 255, 255, 255, which will be white, right? I get my white circle there, and I get my green circles everywhere else. Yeah, we'll go on to things that aren't circles in a second here, but they're just a really easy way to sort of demonstrate what's going on here. And of course, rather than drawing circles just by hand, as it were, with individual lines of code, we can use all the looping functionality we've been learning about to draw circles programmatically. So I could say, for I in range, let's draw 20 circles. PyGame.draw.circle, my color, here, I'll tell you what, let's go from 0 to 400 in steps of 20. Do you remember this range function that we looked at generates a range of numbers from the first to the second? And if we give it a third parameter, that's going to be our step value. So I is going to take on the values 0, then 20, then 40, then 60, then 80, and so on. And then I'm just going to use that value in my function here. And we'll put it at the coordinates I. So we should put a circle at 20, at 40, at 60, at 0, 0, at 20, 20, at 40, 40, at 60, 60, and so on. Let's make them a little bit smaller just so we can see that happening. And there we go. We have our 20 circles laid out across the screen there. Chris says, can I draw a dodecahedron? I could try. It would take a little bit of time. Oh, good. Polymates, yeah, not a weird thing, but an optical illusion. Yes, I'll take that. So we can loop through these things. We can make a list of these things and draw them to the screen. We'll do that a little bit later, but hopefully this is making sense so far. We can just use this function, which takes a surface that we want to draw to, a color, a position, and a radius, and draws a circle to the screen. Questions? As always, that's my excuse for a beer break, but shout the questions out if you've got them. Anyone drinking anything interesting out there tonight? As always, no pressure to drink if it's not your bag, but this juicy IPA is really hitting this. very good. Those seamless scene transitions, yeah. Oh, I don't know if I mentioned. Yes, Nate hooked me up with a Stream Deck, and so now I'm transitioning between things like a madman. I still have this interesting artifact. I think I mentioned this a few weeks ago, where let's see, what is it? The camera that focuses on the computer and the Raspberry Pi capture card are on the same USB bus, and so they have to alternate back and forth a little bit. And so I have that loading bar in there to fill as they're shifting back and forth, which I think turns out actually pretty classy. But in any case, so that's the circle function in a nutshell. These, I should say, so that corresponds to the circle example that is on the website. Of course, I'm writing this one live, so it's not going to be perfectly in sync. But if you're watching this now or in the future and you're like, oh, I wish I could look at the code that makes circles, there are examples that will correspond at least to the basic functions of these. f.glass/the_bash, right? Let's move on from circles a bit and draw something more crazy like a rectangle. Rectangles are actually slightly more complicated to draw in PyGame because the rectangle, or the rect, is a more fundamental object within the PyGame framework. Being able to sort of, have a rectangle of coordinates or a rectangular area is a really useful thing, not only for drawing shapes to the screen, but we might use that same concept of a rectangular area, say, to define which part of an image we're going to put onto the screen, or which parts of the screen have changed and so need updating, or what the extent or boundary of an image file might be, or something like that. So we have this built-in object called a rect, which represents the idea of a rectangular area, and that's what we're going to use to draw rectangles. So let me show you the construction of a rect object here. We'll say, I'm not very exciting with the names, but I'll say my rect equals pygame.rect, rect with a capital R there. And the rect object takes 4 different parameters, just 4 in a row. It takes the x and y coordinates of the top left corner, and it takes the width and the height. So let me write that out here. So it takes the, let me make sure I get the order right, because it does matter. And actually, this might be a good chance to just take a quick glimpse at the PyGame documentation, which is at pygame.org/docs. It's also linked in the description of this video and on the slides. As always, reading the documentation is kind of the best official way to figure out how things work. It's organized by those submodules that we were looking at earlier. So here's that pygame.event module if you were looking for information on how that worked. Pygame.draw. In my case, I'm going to go over here to the rect module. And right here at the top, it's going to say, okay, when you're initializing a rect object, you give it, okay, so it's left, top, width, height, and that creates a rect object. Oh, we could also give it a pair representing left and top and a pair representing width and height. That's kind of nice. That's good to know. So come back over here, and we'll make our rect with left, top, width, and height. So let's make our rect at, say, 50, 200. We'll make it 100 pixels wide and 300 pixels tall. That's going to represent our rectangular shape. And then to draw that to the screen, we have a function which takes a rect object and draws it to the screen. Pygame.draw.rect. And much like that circle drawing function that we saw, it takes a few different arguments. First one being the surface that we want to draw to. In this case, just the screen itself, just the window we're playing with on the screen. It also takes a color. We'll just reuse that myColor variable we were working with before. And it takes the rect that you'd like to draw. So if I run this, and again, I still have my pygame.flip hiding down here. I should have there we go. So that's a green rectangle that starts at x coordinate 50, starts at y coordinate 200. It's 100 pixels wide, and it's 300 pixels tall, which means it actually goes off the bottom of our 480 pixel tall screen a little bit here, but that's fine. So yeah, that's the basics of drawing rectangles. If we change up any of these parameters, if we say start at 0, we make it 50 pixels wide and 10 pixels tall. We have a little rectangle right at the top of the screen and so on, right? So drawing rectangles, very similar. You just initialize a rect object first, and then you use this pygame.draw.rect function to draw these to the screen. Again, relatively straightforward, right? We're giving it some coordinates and some parameters, and sometimes, like I just did, we have to look up what the actual correct parameterization of these things in. But genuinely, and this is true, I know we have folks in the stream who are at all different levels of like their journey toward programming. Since middle school, when I started programming in BASIC on my math teacher's computer, having the documentation open in another tab or next to you, that's just what programming is. And I'm grateful that we live in a time where like it's open in another tab and not open like in my physical textbook, which is where we started with QBasic. But you open documentation, you don't memorize all these things. You say, was it left or top or left? I don't know, but it's on the website, so I'll just go look it up. So read the documentation; it will help you out a lot. So we've done circles, we've done rectangles. There's a bunch more primitive type drawing things, and rather than walk through them one by one, I prepared a little cake baked in advance, if you will, which is the draw primitives example if you're playing along online, which has all of the sort of primitive drawing objects built in here. Palmer says the correct format. That's pretty good. I didn't think it'd be a particularly pun-heavy night, but I should know better than to underestimate this crowd. So this draw primitives example is not terribly different from what we've been doing so far. I define my screen. Oh, it helps if I'm showing you the thing on the screen here. I mean, I'm sure my face is great, right? But this is what you come here for. So screen width and height, which we'll use to make a window in a second here. I also just went through and made a few colors to play with to start. So again, these are red, green, and blue triplets here. So red is just full red, blue is just full blue, green is just full green. And then we have our three secondary colors, right? Our cyan, magenta, and yellow, which are combinations of 2 out of the 3 of these colors. I just wanted to have some colors to play with as we draw a few things, right? And like before, we're initializing our window with this pygame.display.set_mode function, right? So within our loop this time, in addition to our quit code, here's a bunch of the things you can draw to a screen, and we'll look at them at the end here. In fact, why don't I, let's see, I'll tell you what, let's run this, and then I can jump back and forth between the code and the window where we've drawn things as we go through this code, so we kind of can see what each of these things does, right? So the first line here, in fact, let me shrinkify this. Oops, come back. Let me shrinkify this so we can see them on screen both at the same time. And I'll pull this over to get to our pink friend out there in a little bit. We have our circle function, which we know, there we go, which takes our surface, a color, a location, and a radius. So that's a 30 pixel radius blue circle centered at 300x and 200y. We have a line function, which is new for us. Very similar. It takes the surface and a color to start with, just like all these other ones. And then it takes a starting and an ending position. So in this case, our yellow line up here starts at position 50-50, so 50x, 50y, and it goes to position 75x, 400y. Now, it doesn't really look like it's going to 400y, except you can see it kind of nubbing out the bottom down here. And that's because in just a second, I'm going to stomp all over it with this rectangle here. And that's a good point to point out. Of course, these things are being drawn to the screen in the order that you're writing your code. So if you draw a shape and then draw on top of it, you're not going to see the original shape. So here I've got my yellow line extending that I then stomped over in a second with this big red rectangle. The line function can also optionally take this last parameter, which is width. That's why this line is a little bit thick, as opposed to if I leave that out or if I make it 1. Let's just leave it out for now. I'll close this and we'll rerun this code. Let's see, now we have sort of what we might more think of as a line, just a 1 pixel line here. And if I make that width 50, and I'll rerun the code, we can see I get a real thick line, more like a parallelogram in this case. The PyGame documentation notes that the endings, the terminations of lines, are not necessarily super classy. They're kind of squared off, so this may or may not be what you want, but it's an option there if you're just drawing different shapes of line. We have our rect function that we know. We define our rectangular shape with our left side, our top side, width and height, and then we can draw it to the screen with a color and our rectangle. So that's our big red rectangle over here that we know and love. We have our ellipse function. This one's kind of interesting. So this is going to draw our green ellipse down here. And the way that the ellipse function works is you actually define a rectangle for it too, that's going to be the bounding box of that ellipse, so to speak. So it's going to draw a rectangle onto the screen, and then it's going to fit a tangent ellipse within that rectangle, if you will. So in this case, we defined a rectangle that's from, starts at 150x, so 150x, and 300y, so quite a bit farther down here. It's going to be 45 units wide and 90 units tall. And then we say pygame.draw.ellipse, and we draw an ellipse within it. Now, this could be any rectangle. And in fact, what might be interesting is to reuse this red rectangle up here as the same rectangle that we're using to define the boundaries of our ellipse. So when we draw them together, we can see how that green ovular shape is being defined by the edges of that exact same rectangle. Does that sort of make sense, how the rectangle is defining the ellipse? A couple more functions here that are useful and interesting. We can draw arbitrary polygons, right? So we define a list of points of corners. This is going to draw our cyan little polygon down here. So we define a list of XY coordinate pairs. So this is a list of an arbitrary number of points, and each of those points is a list of two objects, right? So just like when we were defining lists a couple weeks ago, we start with our square brackets to define a list, and then each of those list objects, separated by a comma, is itself a little list of XY coordinate pairs. So we start at 450, 300, then 400, 300, and so on all the way around. And then we use our polygon function, which again just takes a surface and a color. We give it this list of points, and it figures out how to draw that filled in polygon on the screen there. So that turns into our derpy little cyan polygon down here. And finally, we have our arc function, useful for drawing curves. Just like the others, the arc function uses a rectangle to define its shape. Although, to be honest, I'm not 100% sure how. Like, so this is drawing this little magenta arc over on the side here, which, first of all, let's bring that x coordinate in some so it's not running away from us too much. Just so we can see it a little better on the screen here. There you are, you little pink arc. So the arc function takes a surface, a color, the rectangle, which let's explore in a second here, a starting angle and an ending angle, both in radians. So think back to your math classes, right? 2 pi radians is equal to 360 degrees. And it also optionally takes a thickness parameter. So this one is 10 pixels thick. But like I say, I actually don't remember how this is the rect function bounding just this arc? Is it bounding like a theoretical circle? So let's play with this a little bit and see what happens. I think the way I'm going to do it is I'm going to first just draw that rectangle to the screen and then draw the arc on top of it, and then we can see what's going on. So I'll say pygame.draw.rect, draw to the screen. Let's do it in red, and we'll use my arced rectangle again, just so we can see it underneath. So let's run that code again, and we'll see. Interesting. Oh, this other rectangle is making it kind of hard to see. Let's go up here and we'll comment out that rectangle, just so we don't have to look at it anymore. That'll help clean things up a little bit, I think. We'll run that again. You remember I threw it in there, but you can comment things out using this, what the kids today would call the hashtag symbol, what back in my day we called the pound symbol. It causes a comment to happen. Oops, I've broken something. What have I broken? Name my rectangle is not defined. Oh, I commented out my rectangle and then I reused it down here. So let's go back. Let's just comment this all out too, so we can explore. There we go. So now we have, okay, so that pink section is the arc, and the red well, that's utterly unlookable. Let's make this a green square. Unlookable? I think that's a word, right? Unlookable? Can't be seenable? So yeah, okay, so we can see, so the rectangle is defining the fullness of what would be the circle if this were an arc, and then it draws only the portion of the arc specified by your starting and ending angle. Interesting. So this is drawing from 0 to pi over 2, same as 90 degrees. Let's draw 3/4 of a circle. Instead, it should fill up more of that square. Yeah, so it fills from 0 degrees, and another convention in graphical libraries is that your 0 angle sort of starts to the right of the x-axis, just like in mathematics. And then he says, the arc missing some pixels? Yeah, the arc is missing some pixels. It's not filling in super well. And I think, actually, I might be wrong, but let's go to our documentation here. We'll go to the draw library. And this is exactly where I pulled all of these primitives from, right? Rect, polygon, ellipse, and so on. The arc function, let's see. was trying to think if there was a note added that the thickness was drawn poorly. There's not, but you're exactly right, Nate. It is missing some pixels. So whatever algorithm they're using to determine like which pixels should be filled in, maybe they're drawing sort of successively smaller circles, isn't perfect. It's not doing as much as it could be. So yeah, that's just a function of the PyGame library, it turns out. The ellipse function, as a last thing before we leave it behind, I think will handle, or not the ellipse function, the arc function, I think will handle ellipsoidal arcs as well. So if you make your rectangle not a square, it will handle, you know, sort of doing ellipses as well. So that's sort of all the primitives that we get to play with. We get squares, we get circles, we get rectangles. Here, let me uncomment some of the things that we commented out earlier. We can see our whole little family of primitives drawn to the screen there. Wow, this is modern art, is what this is. It's actually really kind of hurting my eyes. Between that and the light that are pointed at me, this is a real experience there. Questions before we move on? That's the gist of drawing primitive shapes to the screen. This night's going to kind of be like, hey, here's a bunch of tools to throw on your palette, and then toward the end of the night, we'll start putting them together into some things. As always, as we're going along, if you're like, ooh, could you use that to do this, or could you draw this kind of shape? Let me know, and we'll give it a swing. Dodecahedron, Chris, was like would take a little bit more time than and brain power, frankly, on a Sunday night than I might have, but I'm willing to give anything a shot. In fact, let's do a quick demo. Let's come back. I'm just going to copy and paste my Hello World code into a new program. Oops. I'm going to copy and paste it, and I'm going to show it to you, you lucky folks. Palmer says, can these screen items become clickable? Yes, they can. There's a couple of different ways to do that, and we're going to get some mouse movement in just a little bit here. Mouse movement and mouse clicking and things like that. I just want to do one little play session with our primitive functions here. So let's see. I'm just going to use, now that we know how to draw a few things, I'm going to use some loop functions to draw some fun things to the screen. So I'm going to say for y in range, screen height, so that's going to count from 0 to the height of the screen, and for x in range, screen width, so count from 0 to the width of the screen. PyGame.draw.line. And let's go from 0x, let's see, how's this going to work? Let's do, so this is what I would have when I'm doing graphical design. I have to think with my hands here. So we're going to go from the first point, well, draw to the screen, going to be my color, the starting point, and the ending point. That's our four things the line function takes. Let's go from a starting point, which is always x equals 0 and y, and that will go to a point that is always x coordinates across and the height of the screen. I think that's right. That's what I mean to do. I'm thinking of, I have to save it. Fundrawing.py. What's happening here will become clear in a second if I get it right. Oops. Well, that's not right. Let's see. What did not turn out here? PyGame.screen.color. Starting from 0, y, going to x, screen height. So this is a little tip when you're troubleshooting stuff like this. This is kind of like the delay or millis function of the Arduino world. We have this pygame.time.delay function here. That similarly takes a number of milliseconds to wait between steps. So something is not right. This is not doing what I thought it would do and make a pretty picture for us. So I'm just going to put a little bit of a delay between each of these draws, and that should allow us to see in better detail what's going on, and hopefully let us figure out what is going on. But here's the catch, right? So it is doing that. You can see it actually crashed Python there. It's drawing a line and then delaying. It's drawing a line and then delaying. But, of course, as we learned before, we don't actually see anything show up on the screen until we call display.flip. So it's just drawing all these one at a time nice and slow to a buffer. But really what I want is to put this flip function inside of my loop so that I can see these things being drawn one at a time. There we go. This is something more like what I wanted to happen. Although clearly it's not I wanted to make like one of those figures that you draw like in middle school on graph paper where you have the succession of lines drawing their way across. This one only seems to be drawn only from the origin. Why would that be? Well, let's kill that. For y in range screen height, so that's going to start at 0 and count ourselves down the screen. And then for, oh, you know what it is? I'm iterating through all of these points twice. So this shouldn't be a nested loop. What I really want is a succession of lines. And instead I'm drawing from every point on the left side of the screen to every point on the bottom of the screen. How can I make that clear? I've kind of gone off the rails here, but I think this is an interesting troubleshooting process. And when I get the final product, we'll see it very well. So here, how can we differentiate these different lines that are being drawn? Let's instead of using the same color every time, let's do a random color. This was going to be part of a later demo, but no time like the present to slip this in. We can make use of the built-in randomization functions of Python like so. So I'm going to import from random, the random library, I'm going to import the randint function. We looked at this syntax last session, a couple sessions ago. In this general import statement, I am bringing in all of the PyGame library, but sometimes you just want one function, two functions, one object, two objects. And in that case, it's considered better form to use this syntax where I say, hey, I don't want the whole random library, just bring me in this randint function that I want to use. So I can now say, my color, let's define it in here instead of up here. My color equals, and of course it's going to be a triple of 3 objects, red, green, and blue, right? But instead of making them constant, let's say that they're all going to be a random value between, let's make it so we can't have a black line, let's say between 0, or between 20 and 255 each. So I'll do that 3 times. And this function, unlike some of the other Python functions we've looked at, is inclusive. So this is between 20 and 255 inclusive. So we're going to generate 3 random numbers, make that the color of our line, and draw it to the screen, delay for 100 milliseconds, then display the screen, and then repeat. So that'll hopefully make a little more clear why this code isn't working. Yeah, so it's just drawing a series of lines over and over from the origin, then from 1 pixel down on the Y side, then from 2 pixels down, and so on, which is not what I intended. So let's crash that for a second here. What I really want is a single loop drawing its way through. The starting position should still be 0y, and let's say our ending position is y screen height. I think this will be closer to what I want. And let's decrease that delay just a little bit here. Let's make that 10 seconds, just to make this go a little bit faster in our evening. Now we get this nice variegated curve line. Did anybody else draw these shapes? Like, I have this very vivid memory of being a middle school nerd and drawing on graph paper with a ruler, where we drew like a succession of lines and they made this interesting shape, sort of a curve made out of lines. I don't know. Maybe this was just me, but I thought it was quite fun. So that's quite nice. The only thing I think I would change is rather than doing it every single line, I'm going to go from 0 to screen height, and we'll go, say, every 10 pixels. And let's go back to a singular color. And one thing I like to do when I'm playing around with this is instead of deleting this whole nice line of code that we wrote, I'm just going to comment it out and change it. Equals, so my color, let's make it green, 255, 0. All right, so now that's the shape I was expecting. God, it brings back such memories to do something like that. So yeah, in any case, a little, like I say, a little off the rails. We weren't going to get to randomization so early in the night, but just like starting to see how you can use these very simple shapes to build up interesting objects. Yeah? Cool? Question? I forget who it was last time who called me out that like asking for questions was just my excuse to take a beer sip, and I'm just embracing it. Like, it's totally true, and I like it a lot. Let's move on to a few other things you can draw to the screen, like text. So this will, again, there's a text example on the Electronics Bash page, but I think it'll be more interesting if we just write it ourselves here. So let's go back to this other bit of code. We'll delete a few things. I'll leave this color. That might be useful to us. To put text on the screen, there is a couple of steps. One is to create a font object that's going to be responsible for basically telling PyGame what pixels make up a given word in a given font, and then we can give that object a word and get some pixels back out of it representing that word. This will all make sense in a second here. So let's create a new font. Let's say my font, a really creative name, equals pygame.font. And I'm going to do something called sysfont, which just uses a font that's built into your operating system already. In a second, we'll look at a bit of code that lets you establish through Python what fonts are available on your system to use for this purpose, but just for the sake of getting us going, I will use the freemono.ttf, the true type font called freemono on my system with a font size of 48 pixels. And then, let me see, how do you, I'm forgetting what the syntax is for putting font on the screen, so let's go to the documentation. So we'll come back to our PyGame docs, put an R in front of sysfont. Oh, you're right, Nate, you're totally right, thank you. That's, sysfront won't do anything, sysfont will work a lot better, thank you. So let's go to our font documentation here. PyGame sys. So here, I'll show you what I did. I went to the font module, and it has these various functions, including font.font, creating a font object. And the font object has a variety of methods, including render. That's what it is. So the render method will take the text that you want to render. Let me zoom in a little bit here. Ooh, that was a disaster. There we go. We'll take the string that you want to render. We'll take a true or false variable, a Boolean telling it whether you want to anti-alias or round out the edges of your text, and the color that you want it to draw, and we'll return you a surface in this situation. So if we come back over here, we can say myfont.render. We'll give it some text. Let's say, hi, Palmer, Nate, Chris. I need to give it that Boolean that says if I want to anti-alias or not. I do. It generally looks better that way. And I need to tell it, what color? Let's say my color again. Actually, let's define our color right here. Let's make this just a nice shade of something that goes in there. So, unlike our other functions which drew their states directly to the screen, you may have seen in this documentation here as we were flipping past it, this returns a surface to us. That's what this arrow notation means here, is when you use this function, what you get back, what you return, is a surface object. So we need some way of getting that surface object onto the screen. And this is how we do that. We use a function called blit. So I'm going to say, I'll explain it in a second here. We'll say screen.blit. Let's see. I should assign this to a variable. So I'm going to say my text is the result of myfont.render, hi Palmer, Nate, Chris, true, and a color. I'll say screen.blit, my text, and I believe it takes a location. I'm going to look this up too. This is the challenge of doing all these things live rather than doing the pre-baked examples, as it were, but I'm pretty sure this is correct. Well, if it's not, it'll give me an error. Hey, there we go. Give us a nice yellow text. So hi Palmer, Nate, Chris starts at X location and Y location 200 on the screen. That's the top left corner of our text here. So this screen.blit function is really powerful. It's a way of combining one surface with another. So I said that this font.render function here gives us a surface, but the pygame.display function gave us a surface. A surface is just a collection of 2D points which have some color to them and some information. I made this slide, I don't know why it doesn't say much. It's a two-dimensional area with some image information on it. It typically has a background color, although the background can be transparent. But other than that, it's just a way of holding a collection of pixels. And one of the most powerful things you can do with PyGame is composite these surfaces together to start to make images. And the blit function here is how you composite one surface, one collection of pixels of some size and shape, onto another surface. And because we made our screen surface, or whatever we want to call it up here, with this PyGame.display.set mode object, whatever ends up on this screen surface is what's going to ultimately be shown to the user. So what I've done here is I've said, okay, I'm going to make a font object that's going to know how to turn some text into some pixels. Then I'm going to use it to render some text of my choosing into some pixels of some specific color. That's going to give me back a surface of an indeterminate size and shape, however long it needs to be to hold that text. Then I'm going to put that surface on my screen at the X location and Y location specified here, right? And once I have this surface, I can use this for as many times as I want. I could say blit my text at 0, 0 as well. And if I run that, hi Palmer Nate Chris, hi everybody. So you can use it over and over again. You could as many times as you want. So compositing surfaces together can be really quite a powerful thing. And we'll look at a few more examples here in a second. But I want to make sure that this sort of makes sense, that rather than sort of using one of these draw functions which sort of directly manipulate the pixels of an existing surface, this is actually creating its own small surface and then compositing it, writing it on top of the pixels of an existing surface. And this particular surface is special. This screen surface we've made special because we made it in this way. That says, okay, PyGame will ultimately say, okay, when you call this flip function at the very end, whatever has ended up on this particular surface that we made in this special way, that's what I'm showing the user, right? So that's why this screen function is special. So we use this blit. This blit function is a function of the surface that you want to draw to, and it takes the surface that you want to draw from and a location to put it at. Cool? If that doesn't quite make sense, here, let's do another demo. This is another skipping ahead in the demos here, but that's all right. That's what these nights are all about. I think there's good learning to be had here. Again, I'm just gonna, I don't know what I did there. I made it full screen. Get out of here. I closed the part of the screen where the program actually shows up, I think. I'm just seeing the I'm not seeing the shell. Well, how the heck did I do that? Ugh. Well, maybe if I close it, it'll come back. Save, sure. Saving sounds good. We'll call that test. Wow, that's a new one. Okay, save and quit. Come back. All right, programming, Thani IDE. If it doesn't come back, we're gonna have a bit of a time. There we go. There's all the controls that we know and love. Ooh. All right, so here's our test program. Let's get rid of our font rendering here, and I'll make some surfaces directly. So I'm going to leave our baseline code here, our quit code, our flip code at the end here. Our screen is still the same. Rather than making a surface object with that font renderer that knew how pixels work in a given font, let's make one directly. We'll say so I still have my screen surface here, and I could call this whatever I want. I could call this window. I could call this main surface, whatever we like. Call it main surface. Well, let's call it the window surface, just to make it really clear what this variable is. It's a surface going to be displayed on our window. And down here, I'll create another small surface. I'll say my little surface equals pygame.surface. Create a new surface object, and I believe it just takes one parameter, which is a pair of numbers, which is its width and height. So let's say 40 by 40 pixels. Yeah? Now, so we can see it on the screen, let's put some color in there, and we'll use a method specific to surface objects, which is the fill function. Just say my little surface dot fill, and if I give that a color, let's say blue, so 0, 0, I don't know, 120. That seems a nice tasteful shade of blue. That will fill the entirety of this little 40 by 40 surface with a blue color, and then I'm going to want to blit it to my main screen. So what did I call that? The window surface. So window surface dot blit my little surface, and let's put it somewhere near the center. Right? When I run that code, I should get invalid position for blit. Got an error here. Oh, right, because this is not two separate parameters. This is one parameter, which is a pair of numbers. Let's run that. And we'll see I get my little filled-in surface gets blitted down here to the screen right where I want it. Cool. So not a terribly exciting example, but let me show you some more powerful ways that we could use this. Rather than just writing it once, let's let's make this a little bit more interesting, and then we'll write it a bunch of times. So much like we use the pygame.draw functions to draw to our final surface that was drawn to the screen, I can draw things to these little surfaces. I could say my little surface, let's see, pygame.draw.circle, and give it, remember, the surface we want to draw to. I think earlier I kept saying, you give it the surface you want to draw to, and I feel like you would be very justified in saying, what do you mean the surface you want to draw to? It's just the window. You're drawing to the window. But this is why I was saying that, because you can choose any of the surfaces you've named. So I'm going to draw a circle to my little surface. I'm going to, let's see, what were the parameters that I used? Oh, the color, right? So let's make this green. 02550, a nice green. The center, let's put it at 2020, right in the middle of our surface. And we'll make it radius 5, a nice little circle. Right? So now when I blit that surface to the screen, I get a little blue square with a little green dot inside of it. Nothing terribly exciting. But let's do a few more things with it. Rather than just blitting this directly to the screen, let's do it in a loop. So for x in range, 0 to screen width, and let's go by 50s, so it's a little bit wider than our surface. For y in range, 0 to screen height by 50s, we will blit our surface to a position on the screen corresponding to x and y. And when I do that, now I have a bunch of tilings of the exact same surface being blitted to the screen over and over again. So you can see how using these subsurfaces starts to unlock the ability to draw simple shapes, whether they're made out of circles and lines, whether they're made out of images that we'll look at in a second here, and very simply repeat them, move them around the screen, reuse them in interesting ways. So that was, again, so we're creating a small surface, and then we're blitting, we're drawing that image to the main screen window, the main window surface, over and over again as we define, if that makes sense. I did look up earlier because I realized as I was prepping this, didn't know what blit, like where's the term blit comes from. It comes from the words bit block copy. Or bit block transfer. It's actually a more general term than just putting one image onto another. Refers to any time you are using a function to composite two bitmaps together, really any sequences of numbers, you put them together with some kind of Boolean function. In this case, it's always saying, okay, the pixels from this chunk of this small surface are going to override, or going to replace whatever is in the surface that they're going onto. That would be a blit, a bit transfer from one surface to another, if that makes sense. Cool. Sorry, I have a pressing need to ask for questions. I like to pretend that the citrusness, the juiciness of these juicy IPAs is helps my throat stay loose for all of this talking. I don't think it's actually true, but it's a nice thing to pretend about. So that's a real quick intro to what surfaces are, little bits of things that hold information and data. Before we get into let's get into images here, and for this one, I am going to actually use my pre-baked demo here just to make sure I get the syntax right. This will be the PyGame image demo if you're playing along online. It's going to look very similar to all of the other demos, but we've got a new function to play with. So outside of my main loop here, I'm using this new function pygame.image, so making use of the image submodule, has a function called load that loads a picture, and I previously downloaded a picture of a kitty cat that we can play with. The image itself, the kitty cat image in this case, and I'll show you here, is in the same folder as my program. So here's pygame.image, here's kittycat.jpg. If your particular kitty cat picture was not in the same folder, you could make this a fully qualified path. You could, say home /py/ whatever your folder path is, and it would be fine. But if you're in the same folder, you can just say, hey, I'm looking for a file called this, and your program by default will look in the folder where the program is running. So in this case, I just put my image file in the same folder for simplicity for this demo. So still creating our same screen with our display mode. Chris says dogs better than cats. This is, Chris, I don't disagree. I have a dog and I love her, and she's got a very good Halloween costume already. But this is, after all, the internet, and I feel like having cat pictures is like semi-mandatory. But maybe it's time we break the mold. So once we've used this pygame.image.load function on our image here, what we actually get back is a surface of the correct size to hold the pixels of our image, right? So in this case, my kitty cat image is like 600 by 700 pixels or something like that. So once I have my surface, I can blit it to the screen just like any other surface. It's just that instead of populating the pixels on that surface by using circles or squares or fills, what have you, my load function has populated the pixels of that surface using the image data out of a file. So if I run this program, what I should get, see, Paul, now, see, Chris, that's an adorable cat, right? Like I am a dog person through and through, but that's a good cat. I think we can all agree. So working with images in PyGame is really easy. We can let's see. I think I have another image here that we can play with a little bit more, just because it's a little bit smaller. What do I call it? Guy.png. I'll take that. So the PyGame image library does take images in a variety of formats. Let's see. Yeah. So there's my little guy. Oh, he's so small. Just loaded up in the corner there. Let's move him out into the screen. I guess we could probably call this variable something other than kitty cat. Let's call this variable, do a find replace, one of my favorite tools. Instead of kitty cat, I'll say guy image, replace all. There we go. There we go. And now he's out in the middle of the screen there, and that'll be just fine. Excellent. So yeah, so now we've got our little dude. Let's make our little dude move around the screen. I'm only like, this is not quite the demo how I intended to do this, but I think this is actually going to be a more interesting demo. That also means there's like a 10% chance I get it wrong. If it does, I'll go back to the other demo. It'll be great. The way that you move objects around the screen in PyGame. So currently, let's go back a second here. As soon as we've done our setup code here, we enter into this infinite loop that's checking whether we should be quitting. It puts something on the screen, then it shows us the screen. Then, for the time being, in all these demos, we're putting the same thing on the screen, and then we are, changing the screen again. Then we put the same thing on the screen, and then we move the screen again. So nothing is changing, but we're doing it many hundreds of times a second just because that's what we told our program to do. If we start changing these things on the screen, we'll start to see how these things that we are actually changing things in time, I guess is what I mean to say. This demo, for example, looks like we're just doing something once and then waiting for the program to quit, but we're actually drawing this guy to the screen over and over and over again, hundreds of times a second, as fast as this program can loop. So let's cause something to change in our program just to see what happens. So let's make a couple of variables. Let's say guy x equals, let's start him at 100, and guy y will start at 100 as well. And then down here, we'll draw our guy, not at hard set coordinates, but at the location guy x, guy y. And since those aren't changing, right, should be the same for now. But now let's say every time we go through our loop, we'll say guy x plus equals 1. And remember, this is syntax that just says, okay, add 1 to this existing variable, and then stuff that value back into this variable. So now if I run this, we can see I've got my little guy zooming across the screen there. Isn't that adorable? I could say guy y plus equals 2, and now we'll really be zooming. And there he goes. And that's all well and good. But of course, we have a couple of problems. One is that our little guy runs off the screen really quite quickly. And the other is that, of course, the speed that our little guy is traveling, he's basically moving 1 pixel over on the screen for every time we go through this loop. But how fast we go through this loop is going to be dependent on how fast my computer is running. In this case, our Raspberry Pi, right? If I had a very powerful computer, or maybe even just my laptop with more RAM running, I would move 1 pixel per loop. But on a more powerful computer, he might be zipping off to Timbuktu really quite fast. So what we'd really like is a way to control the rate at which we loop through our loops. Here's sort of a way to control time, if you will, within our program, so we make sure we're always moving at a consistent rate. And thankfully, PyGame has a facility for this inside of the time module. What we will do is create a clock that will sort of regulate the speed at which we move through this loop, and then we're only going to allow that clock to tick forward at a certain speed. And this is how we do that. We will say my clock, another creative name, equals pygame.time.clock. Create a new clock object here. And then within our loop, usually at the very top, but could be at the very bottom, it doesn't really matter, I will say my clock.tick. And the tick function does a couple of different things for us, and we'll make use of them both. One thing is, if you give it a value, if you give it an argument here, this is the maximum frame rate at which our loop will advance. So myclock.tick 60 says, hey, I don't want to call this function any more than 60 times a second. So now our little guy should be moving at 60 pixels a second, no more, if that makes sense. Now, if we're doing a lot of really intense graphics processing here, I guess, can you see that little guy? I don't know how he's showing up on the internet. He's adorable from where I am, but maybe this isn't quite the thing. Just to make this a little bit clearer, I'm gonna actually, maybe I'll replace my little guy with something we can see a little bit better. How about pygame.draw.circle to the screen? It will be how about nice bright green, and it will be at the same guy X and guy Y location. Oops, takes 4 arguments. Oh, and radius, radius 10. There we go. Ah, there we go. Well, that green is a lot easier to see, but we've now run into another little conundrum here. Grenade says I can see him, but he's just a little guy. Yeah, that's fair. Hey, I'll make this circle even bigger. Now we've turned our little adorable guy into a big horrifying green ever-growing snake. So what the heck is happening here? Well, when we were using our little guy, what's not necessarily apparent is that my little guy has these little white pixels in him, but he's also surrounded by a little border of black pixels. You know, he's just drawn by an artist into a little 16 by 16 pixel grid. He has some black pixels to either side of him, and so as he moves over pixel by pixel, he's sort of erasing his own trail behind him. But when we use something like a circle, which very specifically is not drawing any pixels outside of itself, there's nothing to erase the previous pixels as the circle moves across the screen. So what we need to do in this case is, just before we start drawing things, we'll use our old friend, the fill function, to fill the screen back in with black right before we draw our new circle. And that will give us the appearance of moving our circle across the screen. Because 60 times a second now, we are filling the screen with black, then drawing the new green circle, then filling it with black, then drawing the new green circle, and so on, right? So that's a little bit better there. Get rid of I'll move my guy code out of the way here in case we want to bring him back later. We'll just comment that out for now. I guess we could leave him in, but... So now we have a way using this clock function of only moving at a certain frame rate, right? And if we half this frame rate, like if I say, move at 30 frames a second, we're still only moving at 1 pixel per second. So this circle is now moving at, 1 pixel per frame. So this circle is now moving at 30 pixels per second because we have 30 frames per second, 1 pixel per frame, 30 pixels per second. That sort of makes sense? And this is all well and good, except, what we really want to set up is a flexible framework so that, like, if our computer, our Raspberry Pi, or whatever really starts chugging, that the basic actions of what's going on aren't affected by frame rates. I don't know how many of you play computer games out there. I play a little bit of computer games, but take a classic example. Any one of your modern 3D high graphics performance shooters, runners, whatever you have, right? The behavior you want is, if my computer starts slowing down, I don't want the whole game to slow down. I just want it to show me, the image less often. I want lag, right? I want my frame rate to drop and start stuttering, but I want all my physics, all of my actions, all my behaviors to still progress at the same sort of rate of speed. So we can use the other function of the tick function to accomplish that in PyGame. So remember, I said if you give it an argument here, we're limiting our frame rate to no more than 60 frames a second. But if we assign the result of this tick function to a variable, it also gives us back the time in milliseconds since the last time that the tick function was called. Right? So if all is going well, this value will be 1,000 milliseconds divided by 60 times a second, right? But if things are going poorly, this delta time, this dt, this change in time between times to the loop will start to increase. So by using this, this little stopwatch function here to influence our behavior, we can make sure things are happening sort of at a constant rate, even if the screen is not updating as fast. I'll show you that in a second here. Palmer says, my work laptop runs Train Sim World at 7 FPS, actually slows down the game's time clock. That is also a fair option, right? At some point your game might say, okay, I'd rather be running at 60 FPS, but I'm not going to run any slower than this, so I may have to think a little bit longer to make work. That is certainly fair. We won't be building Train Simulator in PyGame anytime soon. I'm sure that's a big undertaking, but so to use this dt, this delta time, this change in time to justify our actions here, what I'm going to do is say, rather than just moving 1 pixel per frame of execution, what I'd really like to say is like, okay, I'd like my circle to move at, let's say, circle speed equals, I don't know, let's say 100, and we'll make sure that's pixels per second, right? Let's say 50 pixels a second, so we're not losing the circle like we lost our little guy running off the screen there. So, right, so rather than having the variable, you know, what we have, guy x plus equals 1, right, which increases that variable by 1 every time through the loop. What I really want it to do is increase it by an amount proportional to the amount of time that has passed since the last clock tick. So something like this. It's a guy x plus equals circle speed divided by 1,000 milliseconds in a second, right? And multiply that times the delta time, which is going to be, you know, some small number of milliseconds. Actually, this might be a little bit more clear to write it. I would say dt divided by 1,000. Right, so I'm taking my speed in pixels per second and multiplying it by the fraction of a second that has elapsed since the last time we went through this loop. So let's say 50 milliseconds out of the 1,000 milliseconds in our second have passed. Then I want to only move, you know, that proportion of my total pixels per second speed. Now there's one little change I think I'm going to have to make this work. I think this will have an error here pretty quickly. Yeah, So you can see this error down here says integer argument expected got float, and that's because this is giving us some float objects, some objects that, you know, might be, you know, 100.0642 pixels, and the draw circle function really wants these to be integers. It wants your circles to be centered on an integer numbered pixel. But that's easy enough. I can just say, okay, I'm going to let my variable continue to have a floating point value, so any decimal value it wants, but when I go to draw it to the screen, I'm going to round it off by casting it to an integer. And you'll remember that this casting that we talked about last time, just saying, okay, I want you to take this float variable, this number variable, and interpret it for the sake of this operation as an integer. Nothing with a decimal point after it, just a whole number for this time. And so if I do that, now we should see, now we have our circle moving across the screen at 50 pixels a second. And if I change our speed, right, change our speed variable up here, maybe 100 pixels per second, and run the code, we'll see now we should be moving at approximately 100 pixels per second across the screen. But what's neat about making this movement based on our sort of delta time here, sort of clock time, is that even if our frame rate starts to slip, or, you know, even if the malevolent god that is the programmer causes the frame rate to be lower, right, we can see we're still we're quite stuttery now, but the rate is the same. The ultimate rate of how fast it moves across the screen is the same as it was at 60 frames a second. It takes about the same amount of time to hit the edge of the screen. In fact, even if I turn the frame rate way down and we get really stuttery, though the updates to the screen are only happening now every half second, the actual speed of the object, so to speak, is the same because it's moving proportional to the amount of time it's had to wait before it gets to draw to the screen again. Chris is 144 FPS. I think we can do that. Let's find out. Oh, can't assign to operator? What have I done here? Did I make a typo for event circle speed? Oh, I accidentally copied and pasted that in there where it doesn't belong. There we go. So that's nominally 144 FPS. I mean, I think my capture card only does maybe 60 FPS, and my monitor certainly doesn't. But the math works out. It's happy to update the position of the circle and draw it to the screen at 144 times a second. Whether the rest of our hardware can keep up with it is not really PyGame's problem, right? So going back to our little guy, let's bring our little guy back. And maybe we should look up. It'll be another fun adventure. We'll go and figure out how to stretch him out a little bit there. So now that's our little guy moving at 144 frames a second, and now him moving at 2 frames a second. But again, moving at the same rate of pixels across the screen. Let's do a little live exploration because I know we like that very much. And then I want to talk a little bit about mouse and keyboard input for tonight. So let's come back over here to our documentation. shrink it just a little bit so I can get around. And so the load function returns a surface, and I'm pretty sure that the way to influence the size of objects on a surface is to change them. Yeah, change the rectangle associated with it. So let's find our rectangle. I mean, I'm kind of just talking to myself for just a moment here, but I think what I can do is there a built-in scale width. Okay, let's try that. So let's come back over here. So here's our little guy, and let's stop our little guy from moving for a second here, just so we can see what's happening. So a little tiny little guy right there. So our guy, remember, is a surface that's being loaded by this function here. PyGame image.load makes us a surface. If I use up here, if I say my guy rectangle equals guy image dot get rect, that should return a rectangle with the same dimensions as our surface. So, you know, if our little guy, I think, is only 16 by 16 pixels, this is going to make a 16 by 16 rectangle. Might be a useful thing to have around. Let's see. Yeah. I can now, I think, directly edit the parameters of this rectangle to modify the size of the image. Times equals 2. My guy rect dot height times equals 2. Let's see if this works. I think it did. Let's amp this up a little bit here. 10 times 10. No, not so much. Let's see. How am I definitely have done this before. How do I scale an image in a surface image in PyGame? Or can I do it in my load function? Maybe that's where I do it. Surface, alpha transparency. No, if this takes too long, I will punt as always. But now I'm just curious if there's a decent way to scale the image here, and I feel like there is. What is it? Is there a transform? Yes. Yes, the transform module. That's what it is. So the transform module has a function called scale, which gives you a new surface back with changed parameters from the old surface. That's what this is. Yes, it's all coming back to me now. Very good. So here's what I will do. Get rid of that rectangle. Goodbye, rectangle. I will say guy big image equals PyGame dot transform dot scale. I'm going to scale my guy image. I'm going to make it 200 by 200, and that's it. So now instead of blitting guy image, I'm going to blit my guy big image, and hopefully, hey, there he is. He's nice and big. So that's the large version of the little guy that I've been playing with this time. And now, you know, just like my other little guy, I can make that guy move across the screen again, only at I think 2 frames a second, at 100 pixels per second there. But that's kind of an adorable look. Our big guy walking around the way there. I'm gonna call him Pip. So we had our little Pip running across the screen, and now we have Big Pip sort of meandering out to the edge of the window there. Well, this is all well and good. It might be a little bit more fun if we could control Big Pip directly with our keyboard and mouse, don't you think? So let's start by using the keyboard. So I'm going to get rid of this this automated running away from us function here, and let's turn the frame rate back up just a little bit here, to 60 FPS, and we'll look at keyboard inputs. And this is going to start to introduce us a little bit back to how the event system works in PyGame. The PyGame, so all of these things are in the documentation, and the PyGame documentation is really pretty good, and that's partly why I recommend this library. Is like, if you have questions of how to do a thing, probably in the documentation. In this case, it's going to be in the key library for keyboard input, which has a variety of methods, but the one that we care about most is get pressed. And get pressed returns, here it says it right here. I don't know if you can read it, I'll read it to you. Returns a sequence of Boolean values representing the state of every key on the keyboard. Use the key constant values to index the array. A true value means that the button is pressed. So here, let's explore a little what that means. So let's say in our program here, I'm just going to say keys, or let's see, key pressed value, just the name of some variable, equals pygame.key.get pressed, right? And then, just for the sake of argument, I'm going to say print key pressed values. And let's slow this down just a little bit here so we're not overwhelmed with print statements. We'll save that, we'll draw it to the screen. And you can see down here in my terminal, at 5 times a second, I'm getting a huge list of zeros. But, and you'll have to take my word for it, as I type on the keyboard here, oops. Oh, as I type on the keyboard with focus in the PyGame window, you'll start to see, I've crashed things a little bit here. Let me try that again. You start to see some ones in my is pressed values down in that function here. You can see some ones popping up occasionally down there. Also things like, you know, the window trying to quit itself. So what this list is literally, it's a 0 if a key is not pressed and a 1 if the key is pressed. It's giving us the state of, like it says, every key on the keyboard every time you call this function, which seems a little bit unwieldy, right? A little bit hard to deal with, but thankfully the PyGame developers have made some constants for us that make things a little bit easier to deal with, because most of the time we really only care about the state of, you know, a handful of keys at a given time, probably, for our kind of programs. You know, in this case, I'm going to use the arrow keys to move Big Pip around. So I'm going to look at the state of the left, right, up, and down keys, and then take some actions based on whether those are pressed or not. So rather than having to figure out where these ones and zeros that represent those arrow keys are in this big giant list, we have some shortcuts. So I can say, so my key pressed values, of course, is one big list, and I want to check the particular position of it. So I can say if key pressed values for some location in that list is 1, or really just if it's any truthful value. So in this case, I can just say if key pressed values is true, then I'll say pass. We'll say do something here, right? So let's say when I press the right arrow key, I want Big Pip to move 1 pixel to the right per frame. And the way that I reference the right arrow key is with this syntax. I say pygame.kwrite. So within the PyGame module, there is a variable or a constant called kwrite, representing the position in this list that the right arrow key is. So I can say, hey, look at this list and look at the position representing that key and tell me about it. If it's 1, this will be true and I'll do something. If it's 0, this will be false and I won't do the thing. So in this case, I'd like to say guy x plus equals 1. And let's run this at, we'll go back to our sort of lazy way of doing movement. We'll move it 1 pixel per frame at 30 frames a second. But now, as you can see, I've got my Big Pip on the screen here, and if I bring up my table view, I haven't used this camera at all, and it's a nice camera. So here, I'll give you the real live action shot of what's happening here. It's a real little pro gamer circuit over here. Get over there. This is really just for my own entertainment at this point. Yeah, you can see, now I have keyboard cam, you can see my speedrun strats. But when I press the right arrow button, you should see, yeah, there he goes. There goes Big Pip. Oh, and I've now got the camera in the camera. Well, it's all very classy. But of course, my left arrow key doesn't work yet. Let's look at the left arrow key working. So I'll say, in this case, and you should be able to guess how this might work. I could say if key pressed values pygame.capital K underscore capital left, guy y or guy x minus equals 1. Move to the left when the left arrow key is pressed. And let's run that. And now we can see when I press the left arrow key, Big Pip moves left. When I move to the right arrow key, Big Pip moves right. Let's speed Pip up a little bit here. Let's say Pip's. Let's call him Guy in the code, but we'll know he's called Pip. So we'll say Guy speed equals 5. We'll say this plus equals Guy speed, minus equals Guy speed, and let's do our up and down arrows while we're here. We can say if key pressed values pygame.k up. That'll be our up arrow. So the up arrow, remember, is decreasing the y-axis. So we'll say Guy y minus equals Guy speed. and if key pressed values pygame.k down, k underscore down, guy y plus equals guy speed. So now when I run that, assuming I haven't made too many typos, yeah, I can move my big pip around the screen. That's very great. Of course, he can still leave the screen and come back. He can run away and come back again. But he works just fine. Now we could implement some other code to, prevent him from moving off the screen or something like that. But let's implement a functionality when I press the left arrow or the right arrow, it turns him around. And then we'll look at some clickable mouse input. Will be the thing that we do after that. I'm going to say it out loud so I remember to do it right after this question break. I was doing so well. That's all right. What I need is to put back in a mute indicator, which I think actually now that Nate's blessed me with a Stream Deck, I think should be a lot easier to make like the mute button not only mute but run a function that I don't know does what, like puts a big red border around everything or a big red light in my face so I can't possibly ignore it. Dang it! All right, well, good. It wouldn't have been a Sunday night if we hadn't had one little Jeff Cole screw up here. Let's make Big Pip turn around left and right when we press the left and right mouse buttons. What do you say? So let's see here. So we have our Big Pip image. That's our guy big image here. So this is going to be really the image for when he's facing right. So it's called this guy big image right over here. And I'm going to get rid of my own hands typing in the corner of my vision here. And what I want is an image of him facing left. So I'll say guy, big, image, left equals, and I bet, and again, making this up as we go, I bet there is a transform function that allows us to flip our image left and right. I would bet my bottom dollar that tomorrow it's the first one on the list. Great. PyGame.transform.flip. So flip takes in a surface, takes a Boolean for X and a Boolean for Y, whether it should flip in the X direction, the Y direction, or both. And that will give us back a new surface with the appropriate flip applied. So let's say that the left image equals pygame.transform.flip of my guy big image right. X flip, so left and right should be true, and Y flip should be false. We only want to flip left and right here. And then down in my conditionals here, what I want to say is if my right key is pressed, then, okay, so yeah, so what I'm going to need is, before I draw my guy to the screen, what I really want is, I'm drawing my guy big image to the screen here, and what I really want is, let's redefine, let's make a new variable here. We'll say image to draw starts as being equal to guy big image right. So originally the image to draw is going to be the rightward facing image, and then every time through the loop, that's what I'm going to draw, is the image to draw. And what I'll do is in my conditional functions here, I'll change which image that's pointing to. So I'll say if my right key button is pressed, I will say my image to draw equals guy big image right. And when my left key is pressed, I'll say image to draw equals guy big image left. Save that, run it, and if I haven't made too many typos, when I pro gamer cam, if I go to the, I've created an error. Very exciting. Guy big image right is not defined. That's interesting. Oh, this is the thing that can happen. So I've caused an error in Python. So now it's not looking for that quit event anymore. I can't actually quit out of my window up here. So I have to go and press the big red button in Thani there. Let's see. Guy, did I get rid of my guy big image right? Guy big image left. Did I misspell something? Oh, I did not spell out image above. It's image. That's just sloppy conventions on my part. Let's run that again. So now when I press the right mouse button, big pip moves to the right. When I press the left mouse button, big pip moves to the left. He can move up and down. If we were being a little, a little more crafty, we could have him have maybe looking up and maybe looking down a little bit when he moves around the screen. But now we sort of have the basics of a little character to move around the screen with. Yeah, that's the basics of keyboard interaction, is you're getting this list of keys that are pressed and reacting to them as they come along. Yeah, pretty cute. So you can imagine, a situation in which we might okay. We're at what, 93 minutes? We can do one little tiny more side demo before we do mouse stuff, and then we'll call it for the night. Just because it'll be, I think, adorable. Let's give this guy some gravity. So what I will say is, in addition to having my Y value determined by my key presses here, I'm going to say that every time we pass through this frame, guy Y, let's see, this might be too much to tackle off the cuff. We need to define a velocity. Getting heavy around here, but it would be kind of fun to take this on. So let's say, let's define a few more variables just because we can. So we'll say guy vertical speed equals 0. And we'll say every time we press, let's say the down button will no longer do anything. And when we press the Y button, I'm going to say guy, not guy's, his position doesn't change, but his guy vertical speed equals 20. So as long as we hold the up button, he's going to go up at 20 units per frame. And then every time we go through the frame, I'm going to say guy vertical speed minus equals 2. I'm kind of making these numbers up. We're going to have to fudge them as we go. And then having adjusted his speed, so his vertical speed is going to be, let's see. So with the Y direction, up is negative, so down is positive. So actually, when he jumps, his speed wants to become it must become negative, and to fall, his speed wants to become more positive. If I were, little side tangent here, if I were making a larger game engine out of this, what I might think about doing, because of course, if Y increases down the screen, that feels kind of backwards to me in terms of how gravity would work. So I might write some additional functions to handle the fact that, like, okay, when I think about Y values, I want to think about them from the bottom of the screen up, do some translation for me code behind the scenes so that I can think about that way. We won't do that for today, but just a little side note. So at every frame, he's going to increase his vertical speed, and his vertical position is going to change by his vertical speed. Let's see here. Let's see if that does. Yeah, So of course he won't stop at the bottom of the screen, and he will continue. He will levitate upward at a constant speed whenever I'm holding the up button here. But now he's got a little bit of gravity to him. Here, let's do one more thing. Let's stop him from going off the bottom of the screen. We'll say if guy Y is greater than. So remember, in our coordinate system, here I'll freeze him in place for a second here. In our coordinate system, the image is being drawn, the coordinates of the image are the upper left-hand corner of the image. So really, when the image gets to, the bottom of the screen minus the height of our guy, which I think is 200. Yeah, 200. So I'll say when, if guy Y is greater than screen height minus 200, guy Y equals, let's see, we'll do a couple things. We'll lock him to the bottom of the screen, equals screen height minus 200, and guy vertical speed equals 0. We'll have him stop as if the ground is there. So hopefully, yeah, now he just sits at the bottom of the screen. And of course, it's not really a naturalistic jump, because as long as I hold up, he will just sort of levitate. But now we've got a little jumping guy who stops at the bottom of the screen and moves around, right? And so, all of this, and, we could be a little bit more formal about our methods. We could probably, take some of these magic numbers, like the fact that he's 200 units tall, and put them into a nice variable. But we did all this behavior in, 20 lines of code, which goes to show you that, like, one of the nice things about PyGame is it's really fast to get little things like this working. And play around with stuff. Next stream we recreate Fall Guys. Oh man, I have not played Fall Guys, but it looks like a real great time. Yeah, Networking would be a whole network, like the network servers and like how you accommodate users in that way would be a whole other topic, and not my area of expertise for sure. So let's move on to our final interaction topic of the evening, which Palmer presaged us with like an hour ago. Back in the we're gonna do a Jeff Glass 90 minutes tonight, but hopefully not a Jeff Glass 3 hours. Let's talk about mouse position and how you receive mouse clicks. So there's a couple of different ways we could handle this behavior depending on what we want to do. Do we want to just detect that the mouse button is clicked down? Or do we really want something to happen when the button is depressed, when the mouse button is clicked, but not to repeat, over and over again as long as the button is held down? And usually we want something to happen just once when we click the mouse, or maybe when we double click, but not something to sort of happen continuously, unless we're making like a paint program, in which case, yeah, every time, as long as the mouse is held down, I want to change some pixels on the screen. But for our purposes, what I want to do is say, okay, every time I click once, something will happen. And we'll figure out something fun to happen here. So here's how we handle mouse clicks in that way. And I'll just build into our Big Pip demo here, because I've kind of fallen in love with Big Pip. Let's add this in here. So the way that we're going to add the ability to detect just a single mouse click, as I promised you so long ago, is to continue to make use of our event system. And apologies, I should have paused for questions in between topics, but I will now. And then I'll unmute. And we're back. In this event system here, so what's happening as our program is going through its loop over and over and over again? It's accumulating a series of events. And events can be all kinds of things. It could be keyboard presses, it could be mouse interactions, it could be network events, it could be files finished loading, all this stuff. They basically get put into a big list for us that we can retrieve with this method pygame.event.get. Just gets a list of all of the events that we've accumulated since the last time we checked. So we're going to loop through them using our Python syntaxing for every event in this list, and then we can choose to do stuff with. And so far, the only thing we're saying is like, hey, is that event a quit type event? If so, quit out of our program. If not, throw it in the trash and move on, right? Now we're going to look for a second type of event, the mouse down event, or the mouse button down event. So we'll say if the event type is quit, exit. Otherwise, if the event type equals pygame dot mouse button down, let's see, then we will say let's make a new variable called click location equals pygame.mouse.get position. And in this case, let's just print that click location back out to the terminal so we can see what's going on. So if I run that code, again, it's the same bit of code, we still have Big Pip, but if I click somewhere on the screen, you can see down in the shell here, I'm getting the XY coordinates of wherever I click when I click. Here, I'll give you the pro gamer view. Oh, geez. Well, if I have enough table space, there we go. As I click the mouse button here, you can see that I'm getting coordinates corresponding to the location that I'm clicking. And more importantly, if I click and hold, I'm only getting the first location that I actually clicked. Because in this case, I'm only going to have something happen the first time I click the button on a location. So let's think of something to do in that location. Let's see what we could do. Instead of printing it, let's print it to the screen just so we can see. Let's start with a simple example. Let's say pygame.draw. Okay. So here's what I was gonna say. Whenever you move to accommodate mouse, can make your mic start popping. Oh, interesting. Hang on 1 second. Is that any better? I moved my mouse over toward my audio interface, so hopefully, and I retightened things there, so hopefully things are sounding a little better. Excellent. I also, so sidebar, and Palmer, I may actually have to tap you for technical support on this. I can't figure out how to get the direct monitoring function for the audio working, although the interface should do it, which hopefully would let me catch something like that, and maybe honestly the self-muting stuff too. Anyway, I promised you this would be our last demo. Let's do mouse clicks. So what I was about to do is say, whenever I click, do pygame.draw.circle, draw to the screen, draw it in a tasteful red, draw it at the click location, and draw it with a radius of 10. Let's say, so I'll click, I'll make an interface, not interface, I'll make a circle wherever I click. But you may already see the flaw in this plan, not in the code, but in the behavior. So though I'm able to click just fine, and though I am, you don't really need to see pro gamer view of me clicking a mouse. Though I'm able to click just fine and get coordinates, those circles are not showing up. And that's because, of course, every time I go through the loop, I am clearing the screen, right? I am, wiping over this circle that I would have immediately just made. So really, to maintain these circles on the screen, what I need to do is not just draw them each time. I need to make a list of all the places I would like to draw circles and then draw them again each and every loop. So rather than saying, using that draw function, we'll move it outside of our if statement for now, and we'll make a new place to hold the locations of those circles. We'll say, let's call it an object list equals an empty list. And every time I click, I'm going to say object list dot append my new click location. And then outside of my loop, I might say, I'll blank my screen here, right? This fills my screen with black. And then I'll say for object in object list, draw a circle at that location, right? So now when I run my code, I should be able to click and place little red circles all around my screen. And this starts to illuminate those black pixels that are around my my pip icon here. You can see him covering up all those red circles with those extraneous black pixels. There are ways within PyGame, I should say, to handle things like semi-transparent images and alpha transparency. We won't get into them tonight, but it certainly is possible that we could have pip, obscuring these red circles in a slightly different way. But does this sort of make sense why just adding a draw function to our if statement here was getting stomped all over by our fill? This is a pretty common pattern where your events add some object or some property to a list or a collection, and then every time you pass through your loop, you're responsible for redrawing the object on the screen that you still care about. Chris says, might be more advanced, so could you make pip move to the mouse clip position? Would mouse clip up make pip then always move to the mouse location? We certainly, let's see, we could make pip move to the mouse location. Let's see how we might do that. So first, I'll just comment out the code for making those little red circles. Actually, let's leave it in, because why not? We can make this do two things. And I'll say for every time we click, I want to, move pip to the location of the mouse. So mouse location, you remember, is this tuple, this list of two objects, and I want to make that the x and y values for pip. So I might say guy x equals click location 0, that first object in our list here, and location 2 equals click location 1, right? So now when I run that code, I should be able to, okay, so this is not quite the behavior I think you probably imagined, Chris, right? So pip's top left corner is moving to that location, but it would feel a little more natural if his center was moving to that location, right? So there's a couple different ways we could handle that. We could just subtract his width and height from these parameters, right? I could say, guy x minus 200, right? And now when I click, he'll be shifted, ooh, that's not quite what I want, right? Maybe he's not really 200 pixels wide. I think that's probably what, thank you, Chris, 100, because of course he's 200 pixels by 200 pixels. Yeah, there we go. Yeah, that feels more like it. So now we're warping pip to, now interestingly here, there's kind of a thing happening. If I click fast enough, he's never hitting the ground, and so he continues to accumulate vertical velocity, right? And then he falls really fast when he goes. So probably another thing we'd want to do here in this strangest of games is say, vertical, what did we call that variable for his vertical speed? Guy vertical speed. Guy vertical speed equals 0. So he starts falling afresh whenever I click. That feels better. And here, let's do one more thing. Let's say when he moves to the right as a result of this movement, he'll stay facing to the right. When he moves to the left as a result of this movement, he should end up facing to the left, right? If I click over here, he should face right, but if I click back over here, it would probably look better if he faced to the left. He's got some kind of portal gun or warping capability or something like that. So what I'll need to do is get Pip's previous position before I move him. And here, I'm going to take the red circles out of this equation so we can see this a little bit better. So I will say previous x equals guy x and previous y equals guy y. This actually is a good chance to show off a little bit of syntax that help clean this up a little bit. Rather than putting these on two separate lines, I can actually say previous x, previous y equals guy x, comma, guy y. And so this will do the exact same thing as we were just doing. So previous x will be assigned the value of guy x, previous y is equal to the value of guy y. This is nice, especially if you're dealing with x, y coordinates. It just like cleans up this line a little bit. You know, this pair of numbers equals that pair of numbers. Piece of cake. These are still two separate variables, right? They're not becoming a list. It's just a nice little bit of syntax to clean up this line a little bit here. So I might say if so let's see. So we'll save the previous locations. We'll move Pip. We'll reset his speed, and then we'll say if previous x is greater than guy x, right? So if he was further to the right and now was to the left, image to draw equals, what did I call that guy? Let's see. Guy big image left. Else, right? So I don't really need to check whether the previous x was less than guy. It's just the opposite of this. I can say image to draw equals guy big image right. And if I haven't made too many typos, now when he warps to the right, he should face right. When he warps to the left, he should face left. Yeah, that works out pretty well. And of course, I still have my move and hover commands in here as well. But now if I can hover him way up off the screen, but if I click, he comes right back to where he was. And then he'll fall down as usual. So that's the basics of dealing with mouse clicks, is you use this event system to check if the event that you received was one of these mouse button down events. Just to continue to elucidate these examples, and then I will let you go home before the end of our second hour is out. Let's do something corresponding to a mouse up event, right? So within our nested if-else statement here, I will say, so if our event was not a quit event or a mouse button down event, I'll say elif event.type equals, what was our syntax here? PyGame dot mouse button up. Let's see, what should happen when we release the mouse button? Maybe he warps back to the ground. Guy y equals, and we'll do the same thing for when he was off the ground here. We'll just copy and paste a little code, one of my favorite things. We'll warp him to the ground and set his vertical speed to 0. So now, and you might need pro gamer cam for this. And hopefully, let me know if the mic got a little squishy there. I did move things around again. So now, oops, invalid syntax. elif event.type, equals, right? Now I can move Big Pip around. I can jump. When I press the mouse button down, he warps there. But when he warps there. But when I release the button, he snaps to the ground. That's not terribly interesting. Maybe, I want to know Pip's origin story. What past is he running from? Thanks, Palmer. Yes, good. Yeah, I don't know. He's, oh, you know what might be fun? Well, we'll save this for another time, but like we could cause the mouse up button event to cause him to maybe change speed or change location. I don't know. Lots of things we can do. You can start to see how we can build all these behaviors together, start to build something really, really fun and interactive. Interestingly, so from my very limited experience in making games in this style, the hard part of all of this is not necessarily the drawing things to the screen, because that is as we've seen with PyGame, that's fairly straightforward. Coming up with ways to like fill the screen with graphics. There are some interesting programs that sort of simplify that process. In fact, I'll show you one as a little bit of candy before the end of the night. No, the hard part is the collision detection. The hard part is saying, okay, in this case I said, well, when Pip is at the bottom of the screen, he's on the ground. But on the ground turns to be a really squishy term when you start to have platforms or enemies or Goombas or obstacles, or maybe there's ladders you can climb. Figuring out whether your hero is on the ground or touching a wall or touching something else can be one of the more complicated things. Thankfully, PyGame actually has some functionality built in to help deal with this, and we'll go into that probably in next week. But that tends to be the hard part, that the behavioral part, that sort of, as you get into like what does the physics of the system actually mean, that's the challenge. Chris, is there a way to read the mouse coordinates? Oh, sure. What we've done here, so we read the mouse coordinates using this, click location equals pygame.mouse.getPosition function. We could call this function at any time. We just chose to only do it when the mouse button was down. But here, let me just copy and paste this, and I will move it outside of the loop so that we're always reading that mouse location. In fact, let's move it outside the mouse location here and do what with it? Let's just move this whole bit of code outside of the click location here. There we go. Gotta fix our indentation. So now, rather than having this behavior of warping to the mouse location be dependent on whether I'm clicking or not, now it's just gonna do it, regardless. Let me make sure this is the right place in the loop. No, I think this is actually one less level indented. So now if I run this code, Big Pip is locked to the mouse location here. There's no option for him to not be. The left-right behavior seems to have broken a little bit here. Maybe I didn't copy that out. Yeah, I didn't copy that out. It's having trouble telling whether to lock or not. And we could imagine a situation where like clicking a mouse button. Oh, you know what might be fun? Let's now that we've got this behavior outside of our if statement, let's here, let me take this warping behavior that changes his orientation outside of the loop as well, and I'll say when I click the mouse the first time, lock him to the cursor, and when you click the mouse again, don't lock him to the cursor. Like, we'll let him roam free. So you can sort of pick him up and put him down. Yeah, you could totally do crosshairs. Here, let's do that's a more interesting example, Chris. Let's do that. So let's see, how do we let's see. I honestly don't remember how you do alpha keying, like how you do semi-transparent backgrounds, although we could look that up. But since we're getting toward the end of the night, maybe we'll put a button in that for next time. But let's let's call my crosshair surface equals pygame.surface. Let's say 30 by 30 by 30. Pygame.draw.line. We'll draw some little lines on it on my crosshair surface. Let's define the color of them. Crosshair color equals, how about white for clarity, 255, 255, 255. Crosshair color. Start position and end position. So let's just do a little horizontal and vertical lines. So how about 0, x is 0, y is 15, to x is 30, y is 15, and we'll do the same thing vertically. Oops, we'll do a little copy paste, the old programmer's friend. We'll do from x is 15, y is 0 to x is 15, y is 30. Let's see. And now, so the mouse button down will still do nothing. We're no longer really drawing these circles to the screen. Why don't I just get rid of all of that for clarity here? And every time through the loop, we'll just do screen.blit my crosshair surface. And we can just put our location getting code right in here, pygame.mouse.getPosition. I think. Let's see if that works. I've probably screwed something up. Oh, no, there we go. Of course, I still need to recenter it on me here. So let's see. What's going to be the cleanest way to do that? Let's say, bring this out a little bit. We'll say mouse position equals get position. And we'll say, inside of our function here, we'll say mouse position. Our coordinates that we're going to send our thing to are going to be mouse position 0 minus 15. and mouse position 1 minus 15. So we recenter our crosshairs, and there we go. Now we have our little crosshairs there. Of course, like I say, I don't remember how you do alpha transparency, so we have that black box there. There is a way. We don't want to jump too far off of things. But yes, Chris, we can certainly make our nice, our tasteful red targeting reticule there. Oh, I still have the behavior where when I release the mouse button, he snaps right to the ground. Maybe I'll pass on that too, and comment that other code out, so that's not confusing things anymore here. So now, yeah, so now he can jump around. Oh, and maybe we put our warping. Oh, we took the warping code out. That's probably for the best. So yeah, so now we're starting to combine keyboard input and mouse position. And we could think about, maybe when we click, we create a coin, and when he jumps through it, he gets the coin or something like that. All the game design things I will leave as an exercise to the reader. But yeah, that is the fundamentals of the PyGame library. As far as other things to look at, that's the wrong mouse. Just to pop into the documentation one more time here, because I really do appreciate how clear it is, to give you a small more overview of things the PyGame library can do. It can deal with music and sound effects really quite nicely. My Raspberry Pi is not hooked up to the sound system of the stream, so that would not be a great demo for tonight, but it can do it. A lot of the other things we've done, key presses, mixer handles like volume mixing in a more complicated way. So if you wanted to have, a spooky horror game where the oozing sounds get louder the closer you get to the gelatinous cube, you could use this mixer functionality to automatically fade things up. And then they have lots of advanced stuff here. You can work with joysticks, the mask libraries for doing those alpha, those transparency overlays. You can write your own shaders with the GFX draw library. Pixel eraser for if you want to write a bunch of raw pixel data to the screen rather than doing like lines and rectangles. You want to manipulate the raw individual pixel data. This pixel array library is there to make that a little bit more efficient. Working with like a web camera or reading a CD-ROM, various other things. I don't know what the scrap library is. Oh, scrap library lets you copy and paste things, right? So if you were building, not so much a game in this, but like perhaps a utility to allow you to draw your signature in a specific format and then import that into something else. Maybe you want to sort of export that to the keyboard as a way for the user to transport that to another program. PyGame can do that. You can use the scrap module to use the clipboard to move data around. And what's really cool about the PyGame functionality in Python in general is like these libraries are written so that they work on Windows, Mac, Linux, what have you, even though like the clipboard works in wildly different ways in all those systems. So a really pretty powerful system here. Touch sensitive stuff, various testing frameworks and various stuff like that if you're interested in playing around. So I guess the punchline is check out the PyGame documentation for more things that you might be interested in doing. I'll close tonight just by sharing a couple of other visualization libraries for Python. So PyGame is, I think is a great place to start because it's all about drawing your own images and shapes and coordinates on screen. Really gets you used to how manipulating graphics works in a programmatic environment. But there are some libraries that are more specialized for certain kinds of visualization. If what you're interested in is drawing graphs, for example, for a wide definition of what a graph is, Matplotlib and all of its derivatives are a really powerful framework for making 2D graphs, 3D graphs, scatter plots, line plots, all kinds of interesting things. These are some images I stole from the internet. It's really powerful. Matplotlib is kind of old in and of itself, and so a lot of people have taken it on themselves to say, well, the generic Matplotlib graphs aren't pretty. I want to make a version of Matplotlib that, like, by default has very pretty formatting. So if you search Matplotlib but pretty, you'll find like dozens of different dolphin and dragon and seaborn and all these things that are like, they basically make the same graphs but with more interesting formatting. In any case, a really powerful library to work along with. If what you're interested in making is basic graphical user interfaces, not necessarily advanced ones, but sort of basic ones, then you might look at the tkinter library, which is Python's wrapper for a library called TCL, which is a basic interface library that's built into a lot of systems. Linux, Mac, Windows again, and this tkinter is the Python library that calls that functionality to do things like make windows with menus and tabs and buttons. They're not necessarily going to be the most beautiful things in the world, but this, for example, this is the this is the tkinter program I've been working on. You can see the timestamp on these pictures here that I've been working on in the past couple weeks. We were retooling how we automate the 727 automation shows at the museum that I work at, and the current automation shows are being triggered by a computer running DOS 6.2. So I'm bringing us into the 21st century by, not creating the most beautiful program in the world, but one that works just a little bit more reliably and approachably than that. So tkinter is not the most approachable library. I thought actually about doing tkinter as the focus of this week because making these kind of GUIs is, I think, really fun and kind of powerful, but there's enough complexity into how this works that I really want to talk about fundamental graphics and object-oriented programming before we get into talking about tkinter, which we may do someday. But so if that's something you're interested in, creating an array of buttons and settings and radio buttons, say, as a configuration program for something that you're doing, tkinter is a good place to look. The links to the PyGame libraries and Matplotlib and tkinter are in the slides, like I say, and in the description of this stream. And I think, unless there are any further questions, that is going to kind of bring us toward the end of the evening. It's 9:04 local time here. That's actually, not our longest, not our shortest, but I feel pretty good about that. Continue to ask out questions. Yeah, Chris, come visit. Well, maybe not when it's safe to do so. Come visit me at work. It's a cool place. I do love my job a great deal. But yeah, and there's more and more Python there. And maybe more and more Arduinos. Of course, the personal tangent during COVID times, there are a lot of things that can't happen in the museum because they're very high touch. So we're using everything we have from high-end PCs to a little Arduino circuits to automate some of the stuff so it can keep functioning even in COVID times. Yeah, the U-boat tour is really cool. Unfortunately, it's a very small space, so it's closed during COVID times. It now has, thanks to yours truly, a motion alarm on the door, so if you try and slip unattended, it will yell at you. Palmer, my audio interface is a Focusrite 2i2. A Focusrite, I think it's a Scarlett 2i2. I'm not 100% sure. I only got it yesterday. It's still a new toy. It's really great. Thanks again, Nate. It really is. It's making a huge difference. Yeah, if anyone ever wants to come and see the behind the scenes at the museum, I because this is public and stayed on the internet, I am not allowed to give behind the scenes tours to members of the public. But consultants and technical nerds, and I think all of you are, I would love to show you my workshop and what's going on there. Yeah, Palmer, let's you and I get on the after stream. Not really a thing. I'm going to bed. I start work at 7 a.m. But sometime soon, let's talk. I would welcome your help. But in any case, beautiful nerds, that's gonna do it for tonight, I think. This has been really fun. I hope this has been fun for you. It's fun to play around with stuff, draw things on the screen, make shapes, start with little animations. Like I say, next stream, so in 2 weeks' time, October the 11th, it must be at 7 p.m. Central Time, right here on this YouTube channel. We're going to continue talking about PyGame and some additional structures that we can start, turning our big pip game into something that has a little bit more structure to it. Maybe he can collect coins, have an inventory, take actions. And then along the way, we're going to talk more about what I keep promising to talk about, which is object-oriented programming. So far, we've looked at some sort of basic data structures like lists and dictionaries and tuples. How can we start sort of making our own collections of data and functions that'll really start to serve us well in general contexts? Thank you as always for being here on these Sunday nights. I have an absolute blast being here with y'all. It's really a good time. I hope you are staying safe out there. I hope you're washing your hands. I hope you are all registered to vote. And I hope you are using this as a way to draw strength to go out and continue to do good things in the world. As always, if you have questions, leave them in the comments of this video or find me on Twitter at JeffersGlass. Leave them in a comment on the blog. If you find my Zanga, you can comment there. I think they close it down after 5 years of inactivity, I found. But you can try. If you can find my Zanga and comment, 10 brownie points to you. Yeah, thanks as always, y'all. It's been a really great week, and I will see you on the other side of my birthday, back here on the 11th of October, right here on YouTube. Thank you so much. See you next time. Bye.